Disruptors and curious minds. Welcome to another episode of Thinking on Paper. My name is Jeremy Gilbertson, builder futurist at the intersection of music, tech, and story. With me, as always, is my quantum entangled friend, Mr. Mark Fielding. Mark, how are you today, sir?
This version in this universe is doing great. All those infinite other versions of me are doing. Some are doing much better than me. Some are doing much worse than me. So I'm
Well,
quite
at least we have
thankful.
at least we have all the options to try and figure out which path works the best, right?
Well, this path is the only one I've got. I will say that for those who have joined us, we were all ready for a deep dive into quantum computing. We bought our books, How to Teach Quantum Physics to Your Dog. Jeremy's got the cosmic code. We were all ready. And unfortunately, due to some kind of hiccup in the space-time continuum of this universe, our guest is not with us.
But he actually is. Mark. You can't. I don't know if you can see him or not, but he did join the right universe. So we'll bring him on very shortly. But let's talk about let's talk about our. I have a fascination with quantum mechanics. I remember years ago. I don't know how I got into the rabbit hole, but something about the aspect of this area of science in the fact that it's almost undefinable in a way or unexplainable in a way, or you almost have to give way to let it be what it is, which to me aligns very well. I'm not necessarily a big regimented rule follower, although quantum mechanics, there's a lot of rules, there's a lot of equations, there's a lot of things that prove all of that stuff. But it's really interesting to me just in theory and that sort of thing. But how do we apply it to this new level of technology that's coming out that is quantum mechanically based, right? In compute and that sort of thing. So we've all been talking about AI. We've all been talking about metaverse. We've all been talking about Web3 and all of these emerging technologies. But I think this one is really one of the most compelling, because we really don't understand it all yet, which hopefully we'll get into today. But also it ties into what I love about quantum mechanics. That's really interesting to me. What do you think? Where's your head sit with all this?
I think you've nailed much of it. I think we talk a lot about disruption and we talk a lot about what the ramifications of the emerging tech is on culture and entertainment. We talk about crypto and blockchain. We talk about Web3. We talk about AR and VR. And then of all of those technologies, kind of for me, sitting behind them is this unknown entity, quantum computing, that has the potential, at least from the little that I understand of it, to completely either vaporize everything else or amplify everything else to such a degree that everything we know and think about it will have to be completely remodeled. I mean, we've all heard about, as soon as quantum computing becomes a reality, that cryptocurrency is no longer viable because it can break the cryptography of even Bitcoin. I don't know if that's true or something that we should be fearful of or not. But if everything becomes kind of the puppet to the puppet master of quantum computing, I don't know if that's actually true or not, but it's how I think about it.
I love it. Well, with those two perspectives, we also want to give a great nod to our friends at Ripple with a WRIPPLE, Marketing's on demand talent platform that helps bring thinking on paper to life every week. They're great supporters of ours. And if you're a brand, an enterprise, large company looking for some marketing superpowers to lean on, especially sometimes we've got fourth quarter budgets that, end up in a little surplus sometimes, or maybe you get a last minute project dropped on your lap. You don't have the internal expertise to pull it off. Ripple's a great place to lean on. I'm on the platform. Mark's on the platform as well, should you determine that our superpowers are valid. So without further ado, Mark, why don't you introduce our guest and we'll jump into this amazing topic.
Okay, is he here? Sorry, I thought that we were guestless, but there he is.
There.
Okay, thank you. Okay, Viroshan, I want to get your pronunciation right. Naicker, is that how I pronounce it?
It's Viroshan, and Naicker is right.
Viroshan Naicker, and
Yeah,
co-founder of Plural, token
yeah,
engineer,
yeah,
mathematician, a background in quantum computing.
yeah,
I could just read your educational certificates. He studied theoretical and mathematical physics before
yeah,
doing a certificate of advanced maths at Cambridge,
yeah,
and then received a PhD in mathematics with a
yeah. I
discipline
did.
field of graph theory and the mathematical study of networks,
Yeah,
amongst other
exactly.
things.
Viroshan, welcome to the show. We're glad you're here.
Hi. Well, I'm glad I'm here too. Um, I I'm normally in South Africa, which has got a 2-hour time difference from the UK, but I'm currently in Germany, and it seems that it was 4:30 and not 5:30 that this was supposed to be happening.
Well,
So,
well,
um,
regardless, we're glad you're here.
yeah,
We are very glad you're
Let's
here.
jump right in. So
let's go for it.
I did a little bit of research on your background, but one of the things that always fascinates me, and we'll dive into quantum mechanics super deep, but we're all dads, right? The three of us you have children, right?
Yeah,
So I read, I think, an old blog that you had put up about how to enable creativity in your children, and this was written
yeah.
a few years ago. Did you have an experiment in breaking plates?
We did actually.
So that fascinated me, right? And um, learning how to kind of demonstrate frustration in productive ways. You reference the Greeks do it, Italians do it, right? We get out when we get
Yeah,
frustrated.
exactly.
But that's a great nugget because Mark writes about being a dad a lot too. I wanted to start there as a
Yeah.
weird curveball. Tell me how that came to life.
Um, well, sometimes you have to stop, not let it out on each other, and like breaking a plate is quite symbolic, it's sort of, so you can think of a plate as, information all put together, and the act of breaking a plate is kind of, um, it's not quite deleting the information, because the information is still there. In principle, you can put the plate back together, but you distort it and you mix it, which is a really interesting way to get into quantum computing,
We're
because
breaking something back into its elemental particles and redistributing it as new potential, right?
yeah, well, quantum computing is really about storing and manipulating information at the quantum level. So, um, if I look at my so if I try to measure my computer, the position of my computer, where with it being in front of me now, I can send lots of photons in its direction, and I can watch those photons come back. And obviously, my eyes are a kind of sensor, and the position is quite constant. But if I would do this at the quantum level, then the act of trying to measure the thing will disturb the thing because the scale is so small. So, um, what's really happening, and what quantum computing and quantum information is saying, is that, first off, information is physical. So every bit of information, I mean, the information stored in the plate, which was about, the structure and surface of the plate all held together, um, like all information happens in physical reality. So the difference is that a hard disk stores a one on, a bit of magnetic area, whereas when you're going down to the quantum level, you're trying to store something on an atom, or on the orientation of an atom, so something called the spin of an atom, or you're trying to store it in the polarization of a photon. So these are things that are really fragile, and so they break very fast when you expose them to the environment. And you've got this trade-off of, here's a cool place to do computing because we can exploit quantum mechanics, and I'll get into that. But it doesn't last very long because it loses all its properties to the environment. So it's like having a plate that disappears quite quickly as soon as you look at it.
Like
Uh,
is it a Planck? The time is, it's when you say it's not very long, it's an extraordinarily finite, tiny fraction of time. No.
Yeah. So the idea is that if you make these things really cold, for example, then you can, when things are cold, it just means that they're not losing energy to the environment. Okay, so the coolest something is, the less it's losing information to its environment as photons or as heat, which means that it's better for storing information. And we know this, like, okay, your computer runs better in the cold.
That's why data centers are cold environments and
Yeah,
that sort of thing, or cool
exactly.
environments. Yep.
So now with quantum computing, what we're trying to do is keep something in its quantum state so we can do calculations on that state, and still be able to read the outcomes of those calculations. So it's two things that are, pushing against each other. One is you have to take the information that's stored in the state, or the calculation that's in the state, and then pull the results of this calculation out into the environment and amplify it so that we can read those results. While during the computation, you want the state to be like quite isolated so that you can actually do calculations on this. So when I was studying, people were slowly adding up to more qubits. So instead of having bits, you have these things called qubits. And the idea is that a qubit isn't just a 1 and a 0. It can be what's called a linear superposition of ones and zeros. So that means that not only can I be a 1 or a 0, but I can also be the probability of being a 1 and the probability of being a 0, or halfway between. So now, in terms of computation, if I have one classical bit, it can only go into two states, so it can be in either 1 or 0. But if I have one qubit, because of this idea in quantum mechanics of linear superposition, you get all of this free space in the quantum mechanical part of the qubit. And so if you start putting qubits together, you don't just get the computational power of classical bits. You're going to end up with so each additional qubit is increasing the amount of computational space by a factor of 2.
So quick
So
question there. So if we look at,
yeah,
I think you said like linear superposition,
yeah,
if we have like a 1 and a 0, and
yeah.
could it be considered the gradient, the varied gradients between that 1 and the 0, not just 1 and what's in between directly at half of a 0, but like almost if you like washed all the bits that were the 1 and all the bits were the 0 into this pool of potential? Is that like what we're thinking about?
Is that the probability?
Yeah, it's so the thing is, so while it's not being measured, you can put a quantum state into something that has an equal probability of coming out a 1 or a 0. Okay, so that's a particular state, and the idea would be that if I put a bunch of these probabilistic states together, then that allows me to do calculations on the in-between space that I wouldn't be able to access if I had them in purely classical states. So it's a bit of a sleight of hand that allows you to then say, okay, well, if I only have 3 qubits, that means that I actually have, um, you know, a lot more room to do an interesting calculation that I couldn't do in a purely classical sense. And what you would try to do is you would run the computation on these qubits and then measure the outcome afterwards to get the result. So you wouldn't.
But don't look at it while it's being done.
Yeah, don't look at it while it's being done. So you get this massive parallelism, which you don't have in the classical computing sense, and because of that, there's some algorithms that are just better on quantum. So there's some algorithms that you can build for quantum computers, which you can't build for classical computers. Yeah, and so in 1994, Peter Shaw, I think it was 1994. The
It
story
was. I
is
looked
that,
it up today. Yeah.
yeah, the story is that he was he went to a party and got drunk and then wrote on this algorithm for factoring large numbers using for factoring using quantum computers, which cannot be replicated classically. So and this is why people are worried about cryptography getting broken and all of these other things, simply because all of what we know about cryptography is based on this idea of one-way functions, which say if you put something through the function, it's very hard to invert it. And so multiplying two big numbers together gives me another very, very big number, and it's hard for me to find the original two numbers without having to, do lots of searching. So at some point, intelligence agencies were offering bounties for large prime numbers just to see if people would, come forth with them to use them to crack codes. So that's one of the things you can do. I mean, there are others.
Well, a
So
lot of our audience are crypto natives. So is that hypothetical situation of Bitcoin is that possible with quantum? Will that be possible, or is that a media scare story?
look, the rumor is that governments are storing data now so that they can break it later if quantum computing becomes widely available. So you intercept some communications which you think is encrypted using some encryption standard, and then you would in turn store it until you would have the decryption capacity available. So like the algorithms that are used in Web3 and in crypto could in principle be broken, but by this time we might switch to other more quantum resistant algorithms. So while people were developing quantum computing, sorry, while people were developing quantum computing, you had the cryptographers thinking about the same problem and trying to figure out, well, what are things that are quantum resistant and how do we build those and which algorithms are quantum resistant? So there is an emerging area called lattice-based cryptography, and this is in principle quantum resistant. So I mean, there are a couple of other things that quantum computing can be done or that fall into this area of quantum computing, and then the other thing that grew up with quantum computing was quantum cryptography. So there's this idea of sending only a single photon down a piece of fiber optic cable, and the way that photons are sent on fiber optic cables at the moment is that they're sent as packets. So if somebody steals some of the photons in your packet, you won't notice because the packet will still be delivered. And so there's an experiment that you can do where you bend a piece of fiber optic cable and you catch the packets, and you can see the data that's moving through it.
So you bend it so the
Yeah.
photons actually shoot through the jacket of the cable?
Yeah, you bend it in a specific way, and then you catch these photons that are coming out, and so you can read the data. And governments have known about this for a while, but quantum cryptography or quantum so single photon quantum cryptography would basically send one photon at a time with your data set, and if the sort of if the packet is the photons intercepted, you just don't receive it because it's only one photon at a time. So people have been doing that stuff for, I guess, 20 years now, and you don't. Yeah, you should never look at a field in isolation. You should look at, okay, what are all the interesting things that are also coming out of this field? And things like quantum key distribution also evolved with quantum computing. And quantum key distribution solves this really hard problem of how do I get two people to have the same key at different locations without copying the key. So the idea here is that instead of writing down the key and then securely messaging it to somebody, or couriering it, you would send entangled photons. And entangled photons mean that when you read the photon at location A, it's correlated to the photon at location B. So you can then use this correlation to create a key on both sides. So think of like between a bank and its backup server. So you create a session key using quantum key distribution, and then you use that key as a way to do standard encryption instead, without having this problem of moving keys.
Is this
This-
like
this almost-
Schrodinger's key?
So that technology already exists, and companies have been using that for a while. I don't know if that company is still around. It's called ID Quantique. It's a Swiss company.
So this points back to a book I read a long time ago,
Yeah.
9 Chains to the Moon, Buckminster Fuller. Really interesting book that he wrote in, I guess, the 40s or whatever it was. But a lot of what he talked about was telepathy, the idea of telepathy, right? Between humans. But like this sounds a whole lot like telepathy in a way, right? Like,
Well, that's quantum entanglement, where things can be light years apart, but interacting together at the same time, dependent on each other, right? I mean,
Yeah.
that's beyond telepathy. That's just insanity.
Yeah, well, it freaked out Albert Einstein and a few other people. So we're getting to physics is about the study of the world, and we're kind of converging between the study of the world and the study of information. And so that's what came out of quantum computing for me, this idea that, like, okay, there's information stored in the world and you have to figure out ways to measure it, but you also have to figure out ways to error correct on that measurement. So there's this whole area called quantum error correction, which is if you're trying to do a calculation on some qubits, you can add additional qubits to correct the errors that would be introduced by the environment into your computation. And so you get this whole new area called quantum error correcting codes. And then in the sleepy little town where I studied, one of the students who was, I think, a year after me, invented the field of quantum machine learning.
that I have not heard of yet.
Yeah, so she invented quantum machine learning in Durban on the east coast of South Africa. And so she's very well known in quantum circles, and people are inviting her to speak. And if we realize quantum machine learning, she will get a Nobel Prize for inventing the field.
Can we make that a little bit more tangible for our listeners? So what does that mean at a quantum level, and what does it mean for? I mean, most people associate language models with like chat and AI assistants doing your work for you. But what would that mean on a larger cultural and business scale?
I don't think people have a good grasp of what problems. So it's like doing computations on data in parallel. That's the big advantage. But you get these exponentially good speed ups, and that's where you spend a lot of time training models. So presumably, like if you can do interesting things on the quantum side and marry that to some classical side, you get much faster times.
Is it
But
all about like the compute power and the time it takes to compute things, or is it deeper than that?
It's about having more computational space, which is a big deal when you study computer science, because what you do is you will study like functions that can be computed in a certain amount of time. So when I'm trying to do a calculation and I say this calculation is linear in time, what that means is that if I take the number of inputs and it grows by 10, the time that it takes also will grow linearly. But it'll also grow by some linear relationship. Whereas if the thing is quadratic and I increase the number of inputs by 10, then the number of computations are going to go up by 100. And if it's exponential, then if I increase the number of inputs by some finite number, then I'm looking at like an increase of, say, 2 to that number in terms of computations. So if I and most of the interesting problems to solve, so searching what is the optimal route to travel every city in the US, for example, which is a variation of the traveling salesman problem. Which is so this is a hard problem to solve because you've got to go through a big search space in order to get the correct answer. And so we have really good algorithms for approximating this problem. But if we could simulate all the possible paths at once, then and come out with the optimal path, then that gives us the way to get the one solution that is correct in this case. So maths is full of all of these problems, and it turns out that they're all equivalent to each other.
Does it? So as I think about this, so the optimum route to travel to every city in the United States, the traveling
Yeah.
salesman problem, is it about the interdependencies between the choices as you do the computation that quantum can handle better than classical? Or
Yeah, so think of it as like being able to walk all the routes in parallel, so and then pick the shortest. Whereas if I'm doing if I try to do this on a classical computer, I can only like my search space is I go through the search space one at a time, one case at a time, or so it doesn't matter how fast I am, I can't do it all in one step. I have to do them in series.
yeah, for example, so if there's 3 routes, if there's 3 cities, like between where we all live, you can map out starting with my city to your city to Mark's city, and then we do Mark's city to my city to your city, and then the final one, right? Where in quantum, we do them all at the same time.
Yeah, exactly. So So this parallelism is helpful for doing lots of different things, including factoring big prime numbers.
It's a good analogy to help understand actually the impact that it could have. It's quite easy to unpack that and apply it to the supply chain or to really anything to have that impact of everything or many things being done at once, where traditionally it's a long in relatively process of this, then this, then this, then this, then this, then this.
Yeah, exactly. So if you, I mean, we have these kinds of problems everywhere. We have optimization problems everywhere. We have network problems everywhere. And mathematicians have been good at creating like good approximate algorithms, but it would be interesting to see, like, does quantum computing lead through to breakthroughs in these areas? And then the other area, which could be quite promising, is you can use a quantum computer to simulate physics, because trying to simulate quantum mechanics on a classical computer results in the same problem, because you're trying to simulate a very big space on something that it isn't designed for. Whereas, it's a lot easier to simulate physics on a quantum computer in principle, because it works the same way as the quantum thing that you're trying to simulate. So, I mean, that's interesting.
It creates a flywheel, in fact. So that very process of being able to do that accelerates what you can do. So, and then you're just caught in the quantum computing flywheel of progress.
Yeah, exactly.
Love it.
I don't know if you know Star Trek Discovery, and in one of the seasons, she's got this like time suit, and everything it's built out of some like quantum computational material that they had. Probably like calculating trajectories back and forth through time in parallel.
Do you know the episode number? Or
I don't
I'll
know
have to
the
look it
episode
up.
number. I know it's Star Trek Discovery. It could be like season 2 or season 3.
I'll put it in the show notes.
That's a great segue as we kind of get towards the end of our timeline, our linear timeline in this set. So science fiction always kind of helps us think about what the future possibilities could be for something, right? Like how could it be applied, and doing it without worrying about all of the rules, like taking some of the pieces, mashing them with a creative idea and a story, and then let it ride. They've been doing it for hundreds of years, right? So if we look at quantum computing, not from pure math, but from a, where could we see this happening and coming to life? We talked about the optimization stuff, but where else do you see people start to see applications of this coming to life in the future?
Well, it's hard to see because quantum computers are very big at the moment, and you've got to keep them quite cold.
How big?
Or depending on what you're using them for.
And you have to use gold too, right? Isn't gold part of it or something?
Yeah. So there's people have used gold. They've used diamond. So they try to trap an ion in a diamond. And then there's all sorts of things done with quantum optics.
How big are we talking? Like, is CERN just one big quantum computer, or like
no, CERN's a particle accelerator.
No, I know, but is it like that size, or the size of a room, the size of a?
So they're the size of the room with a couple of qubits. And what you can do is you can log into sort of quantum computing facilities remotely and run stuff on them. I think there's a Python module called QIS-Kit, which allows you to do that. But yeah, it's hard to see. Like, quantum computing's been around for, I guess, 16, 17 years. They've been working on building quantum machines. They've slowly got better. but it would be interesting to know more about the physical universe through the lens of quantum computing, because that will lead to new discoveries and new technology. Because with at each level that we understand the physical universe better, we get emerging technologies. And so now we're really at the edge of, well, okay, let's understand this at the quantum level, and then maybe, we get really interesting things like, can quantum computing be used to control a fusion reaction in an interesting way? What is the sort of the thing that results from those two things being put together? Or can we do interesting simulations about how to put atoms together and then result in getting new materials?
So like
Yeah.
we're expanding the playground
Yeah.
of creativity in a way, because we're now able to explore the world and the universe through a lens that actually understands the smaller things, right? So example, I
Yeah.
use this with Mark. I've got a desk, a bar top over here, and if I knock on the bar top, my brain, my sensor, my input mechanism perceives that as something hard and physical, when in fact, if we look at it at a quantum level, it's quite a bit different, but I can't process it. Like I don't have the quantum lens in myself, just like traditional computing doesn't, right?
No. But yeah, at some sensors will be able to detect quantum level effects, and there is an area called quantum biology, and apparently the navigation of birds is related to quantum effects. So you can build these biological sensors that do these things.
Do you ever see a mechanism coming about that allows someone like us to put something on our head, just like the new Apple headset or the Oculus, that would allow us to see the world from a quantum viewpoint?
Um, well, it would be great for, say, looking at your dishes and then seeing them as being both finished and not finished at the
Way to
same
bring it
time.
back around.
But
Nice.
Jeremy, do you mean seeing it from a quantum level powered by quantum computing, or are you just talking about having the capacity to see what's happening at the quantum level?
I think you need the quantum computing to make.
Well, I don't know. Like, we probably know less about the human brain than we do about quantum computing. So what you're talking about is, can we build an interface between us and the quantum world, and then use that interface to either interact with the quantum world, or to see the actual world as like in its quantum way of being, which is the actual world is very robust. If you poke it, it doesn't collapse. Whereas the quantum world's completely different. Things only last on very short timescales, and I mean, even just to, I guess we could get an artist who's good at visualization and understands physics to try to visualize this for us. And who knows? Maybe we'll get a quantum metaverse.
Well, maybe like a more practical question. Okay, the first computers were the size of houses, and very slow and very, well, pretty rubbish and naff. And now,
Yeah.
like, we're all doing this on our laptops. Is quantum computing ever going to reach that stage? Is the technology ever going to be possible where we could have quantum computers in our living rooms?
Look, I don't know. There's a company called D-Wave that built a quantum chip, and every couple of weeks, like China or IBM or Google, somebody's setting a new record for quantum chips. But depending on the sort of this the structure that you're using, so it could be as big as a room, or but to get a chip size thing and keep it cold and do quantum calculations on it, I think is a little bit further away than we hope. I mean, I might be wrong. And then the other part of it is but we can have these facilities available, and scientists can have them available as well, and be able to use them remotely.
Almost like how supercomputers kind of came
Yeah,
in, right? There used to
exactly,
be like a
exactly.
centralized computer where you could throw your calculations at or throw
Yeah.
your data sets at, and that sort of thing. Yeah.
Yeah. Look, we have to get really good at keeping quantum states cold and keeping them cold in like a localized environment like your laptop in order for us to be able to use this in a mainstream way, where everybody has quantum computing. And those are hard problems to solve, and they also require a lot of energy to solve them. So
Well, and then also there's the piece of it too, just kind of thinking about this is in summary is like this technology, this capability is emerging. Like you said, it's been around for 17 years or so, right? And it's
yeah,
continually getting better and gonna feed this flywheel of innovation within that. But then you think about it, it's the infrastructure piece, it's the compute piece, and you still have to overlay stuff on top of that for folks that aren't computer scientists, that aren't mathematicians, to be
yeah.
able to use the technology in a useful way. So like quantum applications and stuff like that and software, like that's even a ways off, right?
Yeah, exactly. And I think we're getting closer. It's just it's not. I think quantum computing's been around for a long time, and solving these problems to the extent that we've solved problems on classical computing, it's going to take lots of iterations and breakthroughs by many different teams. So yeah, I can say that I'm optimistic, but I moved out of quantum computing into the world of Web3. So so
Well, our Bitcoin is safe for the time being. I'd, we sh- I'd, l- can I just like ask just a very self-indulgent question?
yeah,
So when I wrote a book called Apocalypse Daddy, and it's about kind of me and my daughter, and one of the reoccurring stories in this book is kind of my daughter's relationship with Schrodinger's cat, and I've kind of like made Schrodinger's cat into a little bit of a cartoon character that's annoying or not there. And
yeah.
but I would just wonder if you could speak on Schrodinger's cat for a few seconds, just try to explain the thought experiment that's going on there and how relevant, if at all, it is to quantum computing. If you could tie it
um,
together somehow.
yeah, so it is really relevant because it's talking about superposition. So just like you can have a qubit between some state between 1 and 0, the Schrodinger's cat thought experiment is you have a cat in a box, and somehow you have something that is quantum, and it releases, I don't know, some poison, and if you don't open the box, the cat can be both alive and dead. Um, but as soon as you open the box, um, you change the state of the cat, and because the act of opening the box in order to measure changes the state, and so that forces the cat to be either dead or alive, which is a fixed state. But in keeping the box closed, you can have this cat in an in-between state. Um, and it's those in-between states that help us do quantum computing.
Awesome.
The power of the space in between things. I love it. I love it.
Yeah, exactly.
This
Exactly.
this is great. So I'm fascinated. I could listen to you talk about this for hours. Unfortunately, we don't have all of that time, but we really appreciate you coming on to shed a little
Yes,
bit of
thank you.
light into this world. It's something that Mark and I are going to continue to explore
Yeah.
as part of this platform. Any final words for folks out there that aren't necessarily quantum native, but have heard the terminology? Like what could you do to spark their curiosity without blowing their mind too much?
Um, I think I think there are lots of resources that you can tap into, many people have talked about quantum mechanics and these experiments and tried to like bring it down into the language that normal humans can understand. I mean, if you want to have fun and learn physics, I would just go to Feynman's lectures.
I love Feynman. Yeah,
Yeah,
absolutely.
or if you want to get an idea of like what it is like to experience the world as a physicist, and read. Surely you must be joking, Mr. Feynman. So you're always like looking at you're playing with a language which is math, which gives you a window into the physical world, and it allowed. In a way, like we can think of math as this complex language, but it's just a way of seeing things that we don't have access to. So we don't have access to like the infinite, sequence of prime numbers, or like we don't really have access to photons, but we can describe them, and because we can describe them, we can understand how they behave, which is quite powerful, and I think quite a long way away from like cave paintings. So yeah, we'll see.
Amazing. I would 100% echo. Surely you're joking, Mr. Feynman. It was actually, that might have been one of my first books that pulled me into all of this. So we'll post that in the show notes and the links. Viroshan, thanks so much for joining us. Your experience and expertise and the way you articulated it was great, and I think will be very valuable for our listeners. Also want to give a final shout out to our friends at Wripple with a WRIPPLE. And you can experience the quantum potential of great solopreneurs like Jeremy Gilbertson and Mark Fielding within their platform. If you need some superpowers in the fourth quarter to help you out, we're not the only people on it. There's over 3,000 specialists in marketing and technology. WRIPPLE.com. With that, I will. Do you have any closing thoughts, Mark, before we wrap up?
No, that's just going to say that that's available in a universe near you. So yeah, get on it.
Amazing. And Thinking on Paper, you can find us www.thinkingonpaper.xyz. All of this will be on Spotify, YouTube, and all the favorite stuff. Viroshan, thanks again. This has been great. See you guys next week.
See you next week.
See you. Thanks for having me. Bye.